Now, once you've got your cosets, usually the next step, you remember, you have in mind, you know the order of your quotient group, right? And of course, the order of your quotient group will be less than the order of your group, right? That's the whole point of, we're in a sense, dividing the group by a subgroup. And so the order of the quotient group will be less than this. And, well, so long as it's not too large, the order of your quotient group will be within the range of what we've already done in analysing how many different types, in other words, non-isomorphic groups of a given order, the size of that group. And we've gone up to 11 now, right? So now this is of order 4, and I was saying before, that means this quotient group is isomorphic either to C2, C4, the cyclic group of order 4, or C2 times C2. Now, if you remember, C2 times C2, that's what you get when the order of each element, now we're talking about quotient groups, so our elements are now cosets. Now the order of these cosets, if you calculate it, and that's worth doing, once you know your cosets, it's usually a good step to find the order of these elements. Right? There may be cosets and hence sets, but they're elements of a quotient group. So as elements, you can find their order. And you'll find, if you find the order of each of these, they're of order 2. Right? And now there was a theorem that we did a while back. When that's the case, except for the unit element, if all the other elements have order 2, then the group, so it'd be this, your quotient group, is, now since it's order 4, but it'll be of this form. Right? And if you have other larger group, you may have more of times C2 times C2. But in this case, the order of our quotient group is 4, so therefore our G is isomorphic to C2 by C2. Alright? So that's question 4. Next one. Okay, that was question 6. I'm doing about half. Well, I think I'll rub out as usual. It's so easy now that I can do it real time. I don't have to switch off the camera. Okay, so question 6 says, again we're in the context of D3, right? So D3, and we've got a subgroup H, which consists of the following elements, E and B. And you're asked to show H not normal. It's not a normal subgroup. Not normal. Okay. Now, I think I mentioned in the theory part of this lecture that during the problem-solving part, we'd actually show that this particular subgroup, and it's obviously a group, right? Because B squared, now it's D3, right? So B squared is E. So this is a group. It's actually a group, very small one, order 2. But it's so we now need to show that H is not normal, right? So all we have to do is find one counterexample where normality is not valid. Now remember, to prove something is not normal, let's just find one of these elements. Now, if H is normal, you'll have something like this. X inverse H, X equals H. And that's true for all members of G. Okay, G is D3 in this case. Alright? So let's try E. So we put an E here. Will we get a member of H? So if we put an E here, will we get either E or B? If so, then that's consistent with H being normal. But like if I put a B, if I take this B here, put B here, will I get something that's that belongs to H? Will the result be E or B? If not, H is not normal, right? So that's the strategy we'll take. Well, let's try E. So we only got two cases, right? So let's try E. Well, can you see that that's just X inverse X? Well, that's just E, all right? Now that does belong to H, right? Because E's a member. So that's consistent with H being normal. Now let's try B. Now this gets a bit harder because remember X could be anything. It could be any member of G, right? It's a dihedral group. Now in general, X is of this form, right? It's the dihedral group. So X could be any one of these, all right? We've got six possibilities. Now X in general is of the following form. It's of B to the I, A to the J. I mean, have a look, right? So A can range from 0, 1, 2. So, and B can be either B to the 0, as here, or B to the 1, B here. So, in other words, I can be 0 or 1, and J, that's the power of A, can be 0 or 1 or 2. So J ranges 0, 1 or 2. Okay? So that's the general form of an element belonging to D3. It's one of these 6. Okay? So let's plug that in to here, and instead of E now, we'll do B. It's harder. Right? So X inverse B, X will be of the following form. Now, if I inverse this, I will get A to the minus J, B to the minus I. Now I'm plugging B in here now, right? So B, and then X, I'll get BI, AJ. Right? Now, these are all powers of B, right? So I'll just get B to power, minus I plus 1 plus I. The i's cancel, and I'll just be left with B. Okay, so this is A to the minus J, B, A to the J. All right? Make sense? All right. Now, now we have three possible cases, right? J can be 0, 1, or 2. So let's do the 3 cases systematically. If J is 0, let's just call this S, right? If J is 0, S, that's just this. S is B, right? It's just B. You see that? If J is 0, that's just E, that's E, so you just look at B. Now B is a member of H, so that belongs to H. So that's consistent. Right? Now let's try J as 1, see what happens. Okay, J is now 1. So we get S, just this. So that's A to the minus, J's 1, right? J's 1. So that's a to the minus 1, b, a. Now what is a to the minus 1? What is a to the minus 1? We did that a while back. Here. I'll just calculate it again quickly. Now we know that a cubed is e, right? So I'll post multiply by e, doesn't change anything, but that allows me to do the following. E is a cubed, right? Well, that's the same thing as a to the minus 1 plus 3, which is a squared, right? So a inverse is just a squared. So I can rewrite this as a squared b a. And that's the same thing as a b a. Right? See, follow that? I just split this into two a's. Now I've done that. Why? Because ABA is, from one of my relations of D3. Remember we're talking about context of group D3. ABA is just B, right? Here. So this just becomes AB. That's my result. Look at that. That is not a member of H. Not a member of H. Right? Now, for H to be normal, this has to be true for all members of G. Right? Well, we've just found an example